It's a pleasure to be here and to tell you a little bit about experiment at SLAC using the second third of what was a 3-kilometer LINAC. This is the Facet 2 accelerator test facility, and we're using that to explore strong field effects in QED, not collective effects, but at the level of individual electrons interacting with many, many photons. So I'm giving this talk on behalf of the collaboration, and in particular, and especially Sebastian Moyerin, who's the spokesperson for it. I should mention that, so SLAC's about, I don't know, maybe 500 kilometers or so away. The LINAC is a few kilometers, and we're hoping to study strong field effects like you might have in things like magnetars and stuff, which are a little bit further away, I presume. But the length scale, if I understand, is not too terribly different, that these might be tens of kilometers or so. I picked this figure not because two of the organizers at least are represented here, but it was the first picture that I saw on the Simons Collaboration for Extreme Electrodynamics website, and it's really pretty. But also because of this just staggering, I call it astronomical number of about 20 times the critical magnetic field. So let me just, in the next couple of slides, I'm gonna spend some time talking about strong fields, because to different people it means different things. Most of the time I'm a condensed matter and AMO physicist, and to us strong fields are about 6 orders of magnitude or more weaker than that. These are really, really amazing things. So we heard about cyclotron resonances, for example. If you think about a charge, an electron, in a 1 times the critical field propagating through that, the synchrotron radiation, the spectra of that, if you just naively calculate, so there's this critical frequency at which half of the radiation is emitted with lower frequency and half is emitted with higher frequency. Well, you would find that that critical frequency is basically the rest mass energy. So clearly something is wrong, and something must fix that. And of course, quantum mechanics and corrections to the usual perturbative type quantum electrodynamics is a part of the solution. If we think in terms of an electric field instead of the magnetic field, then at the same level, which turns out to be about 10 to the 16 volts per centimeter, so this is roughly 1 over alpha cubed times the atomic field strength. This is where you expect Schwinger pair production. So basically, you could do work on a virtual pair if you could separate them by the reduced Compton wavelength and give them an energy of the rest mass, then these particles would become realized. Or alternatively, you could think in terms of particles, they were traveling the speed of light, sort of in an uncertainty time associated with that same energy. If you could supply enough from the field, then you produce copious pairs from the vacuum. We're going to be talking about processes where we're working in electromagnetic fields, so not just a static electric field or magnetic field, but combined. And in that case, you would expect an intensity of about almost 10 to the 30 watts per square centimeter is needed to realize tunneling, for example, of particles out of the vacuum. Okay, now you can't do this in a single plane wave because you can't conserve energy and momentum, so you need to play some games. Also, in terrestrial, as I'll show in a minute, circumstances, we can't reach these fields in the laboratory frame, so we need to make use of relativity to help us out there. But first, let me just talk briefly about what happens to a charged particle in a strong linear polarized monochromatic plane wave. So if you move to the average rest frame of the particle, you'll see this canonical figure 8 type motion instead of a regular oscillating dipole. As things get moving close to relativistic speeds, the Lorentz force will distort the trajectory. And what you see is that you cross twice per cycle this way, once per cycle this way, and this distorted, I think I'm going the wrong direction there, figure there, you can never get more than a wavelength in terms of the trajectory. So basically, as I move up close to the speed of light, the Lorentz force bends very strongly. And what you would get here is very strong anharmonic motion. I'll define this eta parameter in a bit, but it's basically the transverse momentum, normalized transverse momentum. So when that's 1, you're relativistic. And you can go to Landau, Lifshitz, other textbooks, or work this out yourself. It's not too bad. So this is classical. And the whole thing actually is pushed along with the laser field in the direction, so you pick up momentum that way. So what you might expect in the laboratory is that this will not just emit dipole radiation, but higher order multiples and harmonics of the laser frequency. If you take QED into effect, just simple quantum effects, well, you would expect to have finite recoil, especially if the frequencies involved become comparable to the rest mass. It can be very big. The effective mass changes because of this motion. You put a lot of your energy into the transverse oscillations, and you might expect to see that. And so, for example, here shows at relatively low, apologies, A naught is the same up to people's definition of RMS versus peak as eta. So if you're less than 1, you expect things to be perturbative. And so if you look at the photon emission, this is calculations for an initial 10 GeV electron interacting with 1.5 EV photons. You see a huge upshift. There's a kinematic edge here at a few GeV that if things were linear, you couldn't surpass, but then you see these additional peaks here, which come from scattering of multiple photons, okay, into a single very high energy gamma ray. If you go eta or A naught more than 1, then things go from this kind of structured plateau type spectra to a more continuous synchrotron-like spectrum with quantum corrections to make sure that you don't emit if you had also large enough fields that you're close to the critical field. Those will make corrections to this to make sure that you don't emit more than your particle beam energy. Okay. So, how people typically calculate things. They might work in this stress state picture where your propagators get renormalized, your electron propagators get renormalized because you can emit many, many photons. And so we talk in terms of quasi-momenta here, which are momenta of the dressed particle in the field, picks up the effective mass. And so your Feynman diagrams, you wouldn't normally see something like this in your quantum field theory textbooks, but hidden in here is all the interactions with other photons. So this can conserve energy and momentum. You have a electron coming in the field, emits a high energy photon, and you get a scattered electron. So this is responsible for multi-photon Compton scattering, quantum radiation reaction, and other things. You can also have photon decay, which is the same process turned on its side here, where a photon comes in, interacts with the field, and decays into an electron-positron pair. Now this has a threshold because you need to supply enough energy to make the pair. This, of course, does not have a threshold. So multi-photon Bright-Wheeler type pair production and Schwinger in quotes pair production, because this isn't the usual Schwinger pair production, but more like tunneling in the vacuum you might expect to happen at really high fields. And as you heard in the last talk, there's also vacuum polarization effects, which I won't get into here. Okay, so I think these are the only real equations that I have in the talk. We can characterize these field strengths in terms of Lorentz invariance. A naught and eta I already mentioned. This is basically the normalized transverse momentum, or from being sloppy, vector potential. It's basically the electric field times the wavelength of the strong electromagnetic radiation. So this only makes sense if you have an oscillating field to define that. The critical field sometimes goes by chi, sometimes by upsilon. So that's in the rest frame. If you're probing it, say, with an electron, that would be this P nu here. And I can define something similar for photons. It's basically the electric field in the rest frame of the electron times the reduced Compton wavelength. So very similar, except for here it's Compton wavelength, here it's the applied wavelength, and this is the ratio of that electric field to the critical field. So they're just related by a factor of the ratio of those wavelengths, and I put a star here on lambda here. This is the wavelength seen in the rest frame. Of course, the whole thing is Lorentz invariant, but I picked a frame to show you that in. Okay, so usually the laser wavelength even boosted in experiments that we'll talk about is a similar scale or longer than the Compton wavelength when you boost into that frame. And so A naught is typically going to be larger than chi, but it doesn't have to be that way. And I don't think people have explored the other regime very much, but there's situations where you could get there. So I already mentioned this leads to a effective mass shift because of that extra transverse momentum. And because of this, you also see the ponderomotive energy changes. It picks up that extra momentum there. Okay. So where do we find terrestrial sources of strong fields? Sorry, I was just looking at the clock. And in particular, ones where chi is going to approach or ideally exceed 1. So certainly, historically and even recently in relativistic heavy ion collisions, if you have two particles where the combined Z is greater than 137, 1 over the fine structure constant, you might expect in collisions of that sort that this will become important. Something called beamstrahlung. This is a collective effect, so in particle physics colliders, if you have two very dense beams approaching each other, the collective fields can become critical and basically destroy your brightness. There's been experiments on ultrarelativistic electron and positron channeling in crystals at CERN, taking very high energy particles, and they then sense the field of the nucleus as being critical. And for this talk, we're interested in intense laser collisions with ultrarelativistic electrons, and these experiments basically come in two types. One where those electrons are generated in plasma itself, so the laser does two things. One, it accelerates the electrons to high energy, and then you can use another laser to scatter off that and approach these fields. And there's a number of places around the world working on these type experiments. Some people from this community we'll hear from, I think, in this conference. And then there's the approach that we're taking, which is using conventional accelerators, using microwaves to accelerate over long distances particles to ultrarelativistic energies. And so I'll tell you a little bit about the seminal experiment 144, also at SLAC. E320 is us, and Luxi, which will happen hopefully soon in Hamburg. Okay, so just a quick foray into E144 to put things into context. So this was nonlinear QED experiments on the old SLAC LINAC, taking the 46.6 GeV electrons, focusing a 1 micron or half micron laser, depending on what we were doing, and near backscattering against that. And then using the dump magnets for the electron, you can make a spectrometer where the spent electrons are read out in a calorimeter here, and if you're making positrons, they're measured in a calorimeter up here, different charges, they go in different directions. And then there was also a paraspectrometer, which almost worked. And here, sorry, I'm just showing simulations because the data is a little complicated, but nonlinear Compton scattering was observed up to scattering of 4 or 5 or so photons or more. And here I show the Drest-Feynman diagram to remind you of that process. But perhaps more interesting is that, at least interpreted at the time, as a 2-step multiphoton Bright-Wheeler process was observed, where first nonlinear Compton scattering generates a high-energy gamma ray, which then can decay in a nonlinear process where it absorbs enough photons from the field to exceed that threshold. Okay. There's also a process, so-called strong field trident process, which people couldn't really calculate at the time, or so some estimates were made, and the first was assumed. So a number of groups have looked at that since, and that's kind of a interesting phenomena because this involves a virtual photon, and now you have interference terms and it can get quite complicated. Anyhow, so the positron spectra is shown here. I won't go into details about it other than to say that it was unambiguously measured. And it was in a very interesting regime where the rates as a function of either eta, this A naught, the classical field parameter, could be fit to about a 5-photon process, or alternatively, you could fit as a function of upsilon or chi, 1 over chi, as an exponentially suppressed process in terms of tunneling, and they were roughly equally well. And so this was because the A naught and chi were roughly the same and approaching unity. So the laser wavelength was about the Compton wavelength. Oh, it was so close back in the 90s, couldn't quite get there. Now, number of experiments, just a sampling of them shown here, and future ideas where we sit now with lower electron beam energy. So sorry, I should have pointed out this is intensity in the lab frame, A naught on the upper, and then this quantum parameter chi on the vertical scale here. And so the facet sits somewhere down in here where at E320 we can get A naught of a few and chi approaching 1. So this allows you to explore pair production well into the tunneling regime, and also the transition between perturbative and non-perturbative effects in the electron scattering. Here's roughly what it looks like. It's a large beamline. There's a kilometer of accelerator upstream of it, and then as we go down here, the experiments, the collisions are somewhere in this chamber. This is kind of a couple meter scale. There's a spectrometer, these are quadrupoles, spectrometer here, a dipole. Positrons, if we make them, will be detected here, and currently electrons are not in the electron detection chamber, but measured on the dump table, and we hope to have a paraspectrometer installed somewhere soon. We're working at 10 GeV electrons, so the gamma factor is about 20,000, relatively short, but not super short bunches, 20 microns. Wavelength of the laser is about 800 nanometers, or 1.5 eV, 10 terawatts, if you consider the roughly half joule in 50 femtoseconds, and focus down to a near diffraction limited spot size using F2 optics. This is a CAD drawing of what that looks like. The optics, first generation of which came from Matt Zeff's group. We also use electro-optic sampling to measure the relative arrival time of the laser and electron beam. That turns out to be really important. I won't talk about it, but in collaboration with Noam Talhud's group and Weizmann, there's a positron tracker, as well as a calorimeter also coming from Matt Zeff's group. for looking at the positrons. And here just shows a kind of canonical single shot image of the scattered electrons. So we're not measuring the photons yet, but just by conservation of energy, right, we can deduce something about the photons from the electron spectra. What we don't know is if you have multiple versus multiple sequential versus all at once, or some, in principle you have a distribution that the electro-optic sampling can also be used as a beam position monitor, or at least that's what the folks from Boulder, Mike Litos et al. Are trying to do with it. We use it just as a timing diagnostic where we encode space to time. You don't need to know much about that other than it can, on a shot-by-shot basis, remember the electron beam came from about 1 kilometer away, the laser did not, and you need to hit these things within sort of a gnat's hair. So here it shows a typical distribution of that measured timing jitter over a short time. It's about 50 femtoseconds, but there's drifts, there's other things that you have to worry about. So this turned out to be a critical diagnostic for us. Let me just show you some of the early data real quick to give you a sense of both the quality and the challenges. So this was from 2022. Let's see if this works. Okay. So on the left here, this is kind of cheap background subtracted spectra as a function. We're tuning the wave plate to have more and more energy. This was the raw image up top. I say it was a cheap background subtraction because we just subtracted the low intensity from the high. And down here, you might not have seen it. That was the gamma rays, which we just detect as a hole in the scintillator. We can also vary the laser timing, and I'll show you the movie of that. Nope, there we go. And you'll see something kind of funny. Here's both on the gamma rays are dancing around, and here was the electron beam. You see it kind of sweeping from right to left here. That actually turned out because we're focusing the electron beam and we weren't at focus. And so as we miss time, we get a little bit extra momentum this way versus that way. Okay, and from that data though, which was jittery and we couldn't reach the highest intensities, you can maybe see that we're already getting signatures up to about n equals 3. And you can try and estimate the A naught by either the peak heights or the shift in the Compton edges, and we came up with about a half at that point, so roughly a factor of 10 lower than we hoped to do. We made a number of improvements, though, to the laser, to the diagnostics, to everything, and so now I'm going to show you some of the most recent results. And one of the most important, I'd say, changes from the diagnostic standpoint is that Tanya basically found a way to analyze those images on a single shot and in real-time feedback, and for example, look at the ratio of different scattered energies. So for example, 6 GeV versus 8.5, or 6.9 versus 8.5 here, as a function of that arrival time. So you can see within the jitter, there's a huge modulation in the ratio. So this is basically nonlinear versus linear scattering, and maybe here, the 2 photon, here might be 3 photon. And so we use this to, in real time, sort of tune things up, get our feedbacks running, and a difference of about 10 femtoseconds is enough between a very good collision and missing. I should mention for these initial experiments, the laser beam is much smaller than the electron beam, which means that we are also averaging over a range of intensities, which is a challenge that we share with the laser plasma-based sources, at least until we can focus the electron beam to smaller than the laser. But still, we can see some really spectacular effects, including what looks like the transition from perturbative to non-perturbative scaling. So what I mean by that is scaling where, if you had, for example, 3 photons, it would scale the rates like the intensity cubed, or A naught to the 6th. 4 would go another factor of intensity to something that's more continuous looking spectra, which you would expect at A naught much, or at least greater than 1, where perturbation theory breaks down and all these different harmonic orders pile up together. So you can start to see that happening as we change the intensity. We always have this residual edge here. This is the kinematic edge for linear Compton scattering, and that's from the tail of the electrons. And sometimes you can see the second edge here, but then you get this nice exponential tail. And all these, by the way, are single electron shots. And we collect a lot of them, which is good because we still have that jitter and we have to post-select for the really good ones. And on the right-hand side here, I show simulations. Oh, I didn't point it out, but the reason that we have a big blob here versus nice crisp line here is this is a scintillator screen, DRZ, flat screen. This is some GAG crystals that are, I think, a couple millimeters thick and pixelated, and it's much more sensitive, but we don't have the spatial resolution. All this is looking just on that upper part, the DRZ screen, but we have evidence of scattering down to like 4 GeV, which would be many tens of photons interacting. And then here's just some simulations from Robert Holtzapfel in both the perturbative and non-perturbative regime. And the color coding here is not the number of photons involved per scattering, but how many individual scattering events you have. So yellow here is everything is non-sequential at once, 1, 2, 3, 4 photons. And the purple curve here is that you share between 2 different scattering events. And I guess the green one's 3. And then you can see at the non-perturbative limit that you start to become dominated. You have lots and lots of interactions, each of which are going to have these low energies here, involve many, many photons. And this is sort of the quantum radiation reaction regime where you have sort of a continuous loss of energy, but recoil becomes really important. Okay, so, and I'm almost finished. Just wanted to highlight here that actually, interestingly enough, if we just let that electron beam and laser miss time randomly and then plot, for example, the edge, the 2 to 3 photon edge, when the intensity is not too high, you can see a systematic shift to the blue, which is indicative of that effective mass increase. Okay, so here you can see 2 different shots. This bar is the low field kinematic edge. It gets shifted to the red. This is n equals 1 to 2, n equals 2 to 3. All right, so all this that I've shown today, at least on E320, is preliminary. Hopefully we'll get it all cleaned up and out for publication soon. So let me just give you a sense of where we're headed, sort of near, medium, long term. So we're working on analysis, and we means mostly the students. So that's things like improving the background subtraction strategies. We have a couple different methods that are consistent, but showing some potential systematic errors. I think that's well under control. And then quantitative analysis of the electron spectra as a function of the different beam parameters. Of course, comparison with various levels of simulations. And I didn't talk about it yet, but we did take one positron run where backgrounds were low enough that we had a possibility of seeing something, and currently the Weitzman group is leading, well, it's their detectors, and they're leading the effort to analyze that, see if we have something. Okay, so there's various improvements, additional ones to the spectrometer, beams, etc. Hopefully we'll install the gamma ray spectrometer soon, which will give us complementary information by measuring the energy of individual photons. Laser upgrade, we've been wanting to do this for years. Maybe results will inspire someone to give us the money to do so. Increasing beam energy, in principle, chi goes linear with that, so even without a laser upgrade, if we could get up to 13, 14 GeV, that would be a lot, and then maybe second IP for true gamma-gamma, and so on. Okay, with that, I think I will finish with a maybe close to correct snapshot of the E320 collaboration. This is what I had. The people in bold were involved certainly in the most recent running, and I took plots or analysis or other things from them for this talk. And I thank you very much and look forward to any questions you might have.
Okay, thanks for this very nice talk, David. Some really nice results. And it's great that E144 is getting a sequel 30 years later. Yeah, but good things come to those who wait. So the talk is now open for questions or comments. So we have plenty of time. And I believe there's lots of coffee, so there's no need to rush out. We're done.
Oh, it's perfectly clear.
So you are reaching E greater than E crit.
So
quite in the rest frame of the electron.
Yeah, so we're probably not there yet. We're maybe about halfway there.
Could you just summarize what are the key things you want to? Uncertain, some people are still interested. QED, of course, people think they know. But what are the key things? A lot of things you talked about.
Okay, so this is.
What are the key things? Most exciting thing you want to see, like in terms of physics.
Okay, so this is a really good question. Indeed, QED is our best understood theory, right? I mean, it works so well because it's a perturbative theory in the fine structure constant, which is much less than 1. I don't expect to see something beyond QED, although people have proposed experiments that could look for beyond standard model type things in similar conditions. I think more interesting is just that because this regime involves the interaction of so many photons, just the way that people calculate it always relies on making approximations. Either you're treating things as plane waves and trying to build up from 1, 2, 3, 4, hundreds of photons, or making approximations like the local constant field approximation that treats things as static. And those things should be and need to be tested. But also, my own interest is more phenomenologically what type things can happen in very strong fields. We know that from atomic physics, things like high harmonic generation and above threshold ionization. I don't know if those are familiar things to the audience. If you think back a couple of years to the Nobel Prize in attosecond physics, this is sort of the technology or the phenomena that led to that. Those things, we understand them really well now, but turned out to be kind of, surprising and led to huge new fields of physics, I would say. And you could have similar phenomena with QED as well. We just replaced the atom with the virtual pairs in the vacuum. And so looking at collective effects, so Sebastian in his thesis independently basically discovered things like ATI and high harmonics, where you could have coherent recollisions. So if you got A naught upwards of hundreds or something, you could imagine making pions or muons pairs well below the critical field. Maybe you could do some interesting tests of CPT, or I don't know what you could do, but phenomenologically, that would be really exciting. So that's my long-winded answer to your short question.
David, so you did not talk about detections of positrons. So you don't have diagnostics yet, or the experiment does not produce positrons yet? Or maybe you could quickly summarize.
We have positrons. The question is, where do they come from? Okay, so there's two diagnostics for the positrons. Where one was basically the optical equivalent of the calorimeters that were used for E144. There was so much background originally that these things were basically useless. Things are better now, but we still aren't using them. So instead, there was a series of solid state electron detection, CMOS type technology, Alpine, if anyone's familiar with that, chips. So there's a number of layers of these chips, and when the particle goes through, you can do tracking. And it turns out if there's not too many tracks, you can figure out where things came from and reduce background. The problem is that anything coming down the pipe, you hit a few electrons hit a wall, or I don't know, even residual gas, or something that's not the laser, they can produce positrons. They come around along for the ride and can cause huge backgrounds. So this is being recorded, so I don't want to say where they are with this, but we had some running where backgrounds were low enough that you could manage it, and looking systematically now, blindly I should say, at laser on versus laser off events to see if there's a statistical difference. I expect in the future it's going to be much better, but so
what's the result?
The result I can't tell you. I don't know.
How many?
There are positrons, I can tell you that, but from the laser I can't tell you. I don't know. So stay tuned.
Thanks for a very nice talk. The synchronization that you're achieving is absolutely amazing. I mean, mind-blowing to me. These tens of femtoseconds. What in the experimental design actually requires that? I mean, presumably that means the allowed interaction region must be extremely small. Why is that?
So it's for a couple of reasons, but mainly because both the electron beam and the laser beam are pulsed, and the laser in particular, to get very high intensity, we need to compress it to a very short pulse. And then because we want to take advantage of this Lorentz boost, they're effectively counter-propagating. So we focused this short laser pulse down very tightly with our optics, and we're also focusing the electron beam, which is not quite as small or short, and they just have to pass through in space and time at the right place. In that little sort of, say, few micron cubed, yeah.
What is the collision angle that you actually have there?
So
you showed it earlier,
it's roughly 30 degrees from backscattering, a little less.
Imagine it's very easy to miss.
It's extremely easy to miss. So I didn't show you all the various methods to find it in the first place. You gain a little bit, but you have some other problems, including with the optics getting in the way, so you have to drill a hole in it. But mainly we opted not to do that to help with the focal averaging, because if you cross at a small angle, you don't lose too much in the electric field. It's a cosine effect. But you can, at least when we shrink the electron beam a little more, you can get through the focus a little more cleanly and have less sensitivity to that. If you come on like this, everything sees everything, right?
Are there any further questions? Louise?
Maybe you don't want to go on record on this one, but if you wanted to upgrade your laser, going to an A0 of 10 is not that much. What's the...
Oh.
Is this a space issue or a money issue?
I'm happy to go on the record for this one. Okay, so it's a combination of things. One is definitely a space issue. So this experiment, I mean, it was really only possible because Facet was there. They had a laser, they had the electron beam, but they had, most of what they're doing is laser plasma acceleration and related things, so they had a relatively modest laser, only 10 times the intensity of what we had in the 90s, although in different technology. So, and it's in a little bitty room that's, whatever, a fifth, a sixth of this room with limited utilities and such. Upstairs, you have to go down to the accelerator and everything. Okay, so space is one of them. Also, in the accelerator tunnel, all these experiments are done deep underground with the sewer. There's not a lot of room. I guess you can't see it on here, but somewhere back here, this is the compressor chamber, the vacuum compressor chamber for the laser. Ultimately, that's going to limit us to how big of a laser we can put, because unless we're really clever, we can't fit bigger compressor gratings in there. And there's having to change the optics, a number of things. None of those yet that I mentioned was money, but of course all of them are money and time. So if we have money, we have time and interest. Let's put the pedo out there, right?
Okay, well, let me ask something. Just thinking about some connections with the previous speaker, everything that comes out that you measure, the electrons, gammas, positrons, we hope, exactly what comes out is very sensitive to the exact structure of the strong field region, right? And for a laser, so that's peak intensity. You mentioned, inferring A naught, but size as well and shape of the focal spot, all of this stuff. I'm sure there are similar conditions in a magnetar, exactly what the shape of the V field is. So maybe if you comment a little bit on, how exactly do we extract information about the laser at the collision point to compare with our models?
Well, I'm glad you referred to the magnetars, because I think, but maybe someone can correct me if I'm wrong, our problem, which is a huge problem, might not be as bad. But no, it's actually a real challenge to know what the focal volume looks like. We can make various measurements, which are not ideal, of the pulse length, of the spot size at reduced intensity, and so on and so forth, and try and put it together. Big error bars, bigger than most people probably want you to believe. We can possibly use the physics itself to try and pin this down, which might sound like a bad thing to do, but if you have some independent measurements, and in particular, I think the ability to scan things reliably from low A naught, where we know the physics really well and the approximations are at hand, to higher, that's a reasonable thing to do. But there are some ideas for high-intensity diagnostics that are completely independent. I haven't seen any that work, or I don't know of any, at least.
Okay, if there are no further questions, then I suggest we thank David and Dong again.